Hello, my name is Henry Story. I will be giving here a short, but hopefully mostly complete, introduction to the semantic web, by grounding it in a simple but powerful use case to help connect software agents and people. I'd like to start by looking at the problem of the mythical man-month, first treated by Richard P. Brooks in a very influential article published in the 70s. In this article, he described how adding engineers to a software project does not, as had been supposed, speed up a project, but can in fact slow it down. Richard P. Brooks explains this surprising slowdown as being due to the communication overhead of adding new people to a project. Engineers who would otherwise have been coding have their attention diverted to answering questions the newcomers inevitably have to ask. Some of these questions are as basic as the following. Where is the code? What bugs have already been filed for this project? Where's the mailing list? Where is the website, wiki? What other packages rely on this package? Where are the translations or the documentation? These are just some of the simple questions that inevitably are going to get asked. I'm not even taking into account more complicated questions such as what algorithms are being used and higher level and more abstract questions. In any case, the question remains as to how software development costs can be reduced. Open source provides one very attractive cost reduction: labor. Indeed, freeing up the code makes everyone who wants to participate a stakeholder in the code. Of course, this will also tend to increase the problem of communication overhead. Contributors of patches to open source code often only have a tangential interest in the libraries they are fixing. They need the library to get another project of theirs working, and in the process can be of help. The easier and faster it is for them to get the basic questions answered, the more people will be able to participate, and the faster the code will evolve. This has to be achieved in a distributed network with no overarching controlling authority. So much for the problem statement. Let's see how we can solve it. First, let me introduce syntax, semantics, and ontologies. Consider the sentence, "Henry knows Tim." This sentence is true in exactly the same situations as the German sentence, "Henry kennt Tim," or the French sentence, "Henri connaît Tim." We could understand the XML or the Java on the slide as making the same statements. These are all ways of saying something about the world. To be more precise, they are stating that there is a relation between a person called Henry and a person called Tim. In the diagram I have represented Henry as the simple stick figure, Tim as the stick figure with a hat, and the relation as an arrow going from Henry to Tim. But I really would like us to think not in terms of these stick figures, but in terms of real people. I am Henry. Imagine that there is an arrow going from me all the way to wherever Tim Bray happens to be. We are real objects in the world. So is the relation between us. English, French, German, XML, and Java are syntaxes, which when combined with the semantics, how the names in the sentence relate to the world, permit us to make statements about the world in those languages. Now, Tim and I are not related in just one way. There are many relations between us. For example, the relation of me being younger than Tim, or of me working with Tim. Arguably, between any two objects, there are an infinite number of relations. We therefore need to name these relations clearly if we want to distinguish them. Now, the web gives us a perfect tool to name things clearly and uniquely: the URI, or Uniform Resource Identifier. The best known URI is the Uniform Resource Locator, or URL, which everyone is familiar with. We already use URLs to uniquely name web pages around the world, and we are now going to use them to also name relations between things. This is the cornerstone of the semantic web, and it is really worth taking a little time to consider its implications. First of all, a URL such as the one we have chosen for our knows relation, http://xmlns.com fof/0.1/knows, contains a domain name, xmlns.com, highlighted in green on the slide. This is what allows us to be clear about who the naming authority is. It enables us to find a legal entity responsible for the name, and thereby resolve naming conflicts, if any arise. Secondly, and this is perhaps the most interesting consequence of using URLs as names, the naming authority can place a description of the meaning of a name at the end of the URL. This is the case for the above name. If you enter it in the location field of a browser, you will get a human-readable representation of the meaning of the relation, i.e., a nicely formatted HTML page. When we type the name of our knows relation into Firefox and hit return, the server redirects us to the page pictured here. It says first of all that fof_knows is a property, which is another term for relation. Fof, by the way, stands for a friend of a friend. Further down, it specifies more precisely what types of things fof_knows relates, in this case, fof_persons. And it also gives some definition in English of what the relation stands for. Let me read out the main paragraph. We take a broad view of knows, but do require some form of reciprocated interaction, i.e. stalkers need not apply. Since social attitudes and conventions on this topic vary greatly between communities, countries and cultures, it is not appropriate for fof to be overly specific here. It would be quite easy, technically, to return a page describing the same relation in German, French, Japanese, Chinese, or any other language, set as the favorite in the browser preferences. But even more interesting is that we're not limited to descriptions of the relation in English, German, French, or other natural languages. We can also retrieve machine-readable descriptions. So using the command line curl tool, we can type the command highlighted in green into our shell. This does an HTTP request on the xmlns.com server, but adds a header saying that we would like our document in RDF XML. The result is a well-defined XML document that can easily be consumed by applications. Somewhere in the body of the return document is a section concerning the fof_knows relation we've been speaking about here. This I have highlighted in yellow. So we have both human-readable and machine-readable descriptions of our relation available by knowing just one thing, the name of the relation. Let me suggest that this is as close as we can possibly get to self-describing metadata. Okay, so back to our example. To make the slide more readable, let me start by using the fof namespace abbreviation. Here we see Henry and his fof_knows relation to Tim. Henry, Tim, and the knows relation are what we know in web architecture as resources. And resource is the R in RDF. RDF stands for Resource Description Framework. It is the framework whereby we think of objects and relations as resources, statements as directed relations between two resources, and we use URIs as names. It's as simple as the picture on the diagram. We can relate physical objects in the world, but that is not all. We can also use relations to relate objects to string literals. Here we relate Tim to his name. We can relate objects to resources on the internet. Here, for example, we relate Tim to his very popular weblog. Here are some further relations relating Tim to a couple of his email addresses and to an image. So out of interest for symmetry, let us add these descriptions to Henry. We now have a very good partial description of both Tim and me. They may be partial, but they are good enough to identify us, even though we ourselves don't have URLs. So we can identify things by description too. We can also relate things to their types. Here, both Tim and me are of type fauve person. Fauve person is just the set of all things related to it by the RDF type relation. It is a class. Hence, I have used the UML notation of a class to illustrate this. In the method section of the fauve person class, I have listed some of the relations available on objects of that class. Some that we have not yet seen are fauve geek code or fauve interest. There are many more. Here we relate Tim Bray's hat picture to the fauve image class, of which it is an instance. We can also use the UML notation to illustrate that the fauve::img relation is a relation between objects of type fauve person and objects of type fauve image. Furthermore, we can relate classes to their superclasses. A fauve person is a fauve agent. A fauve image is a fauve document. In RDF, a class can have multiple superclasses. In the same way as in Java, an interface can have multiple superinterfaces. The UML elements on the golden background is what is known as an ontology. They are described using relations from the OWL vocabulary, which is a W3C standard that was finalized in early 2005. OWL simply stands for Ontology Web Language. In any case, the UML diagram should be very familiar to object-oriented software engineers, and this is part of the point I wish to make. There is nothing magical about semantics and ontologies. I would like to look now at how ontologies can help us ask the right questions. To do this, let me first introduce you to a very interesting ontology called DOAP. DOAP stands for Description of a Project, and it is being used by O'Reilly in their CodeZoo project, which I will describe a little later on. The main class of this ontology is, of course, the project class. It has a number of useful relations. The bug database relation that relates a project to a bug database given by URL, a maintainer relation that relates the project to a fauve person, and a home page relation, among others. Notice, by the way, how easy it is to mix ontologies. The DOAP project class has a number of relations to fauve person objects. Here I have highlighted the developer, maintainer, tester, helper, and translator relations. All of these roles are usually filled by human beings, hence the typing of the relation. This is very similar to what we have in Java, where classes can define methods which take objects developed by people in other organizations as arguments. The URLs we use as names give us a distributed namespace that allows clear attribution of responsibility, concurrent development, and easy reuse of the work of others. So here I have filled out the UML diagram for our dope ontology. I have added a dope repository class that has a number of subclasses such as CVS repository and Subversion repository. Notice that dope project is defined as a subclass of FOAF project. In any case, there's certainly a lot more concepts and relations one could develop in this space, but apparently this was useful enough for O'Reilly's Code Zoo. Once we have descriptions of what types of things there are and how they relate, it becomes easy to ask questions. Now that we know that projects have maintainers, developers, etc., we can ask questions such as what projects someone we know is involved in. Asking questions is what Sparkle has been designed for. Sparkle is a recursive name, and it stands for Sparkle Protocol and RDF Query Language. It is about to be standardized by the W3C. As you can see from the example here, it is very similar to SQL. We have the same select clauses, the same where clause. There is no insert clause, by the way, as Sparkle is currently read-only. This example starts by specifying a couple of our prefixes, FOAF and dope, to make the rest of the query easier to read. This particular query asks us to select three variables: who, did, and what, where who is of type person, what is of type project, and did is any relation known between projects and people. Because the result could be huge, we ask to limit the answer to the first 100. It may occur to you now that ontologies are a little like database schemas. Posting the previous query to a Sparkle endpoint should return an XML document such as the one shown here. Notice that the head section names the three variables we defined in our query. This head section is then followed by a results section that contains a number of result elements. Each of these result elements will contain a binding for each of the variables. You can think of this as returning a table of results with as columns the variables, and for each row one possible answer to our query. If you want to play with a Sparkle endpoint, I suggest having a look at the UniProt Sparkle frontend that sits in front of a database containing 300 million facts. This diagram is a confirmation of our previous intuition concerning the similarity between database schemas and ontologies. It is taken from a web presentation by Tim Berners-Lee and illustrates another way one can think of the relation between the triple structure of RDF and the table structure of relational databases. There are a number of ways of storing the triples of RDF. The simplest way is to store them in XML RDF files and place those in a file system or on the web. This would be a bit like doing an SQL dump of your database and placing that online. Except of course that because RDF uses URLs for names of resources, the information is completely defined. As a result, it is possible for this information to be inserted into any other database without the danger of name clashes or information mangling. A FOAF person is a FOAF person everywhere. A person column, on the other hand, in one database may have nothing to do with a person column in another table of the same database, let alone another database. Another way to store triples is in pure RDF databases that are optimized for the graph structure of RDF. There are already a number of such databases. Sesame and Kowari are both written in Java and published under an open source license. Sesame under an LGPL license and Kowari under an Apache license. Kowari is currently sponsored by Northrop Grumman. IntelliDimension is a database written in C and running on Windows. 300 million facts from the UniProt database have been put online behind a SPARQL interface using that database. I really recommend playing with it. Of course, one can store triples in a relational database too. Sesame, Jena, and Oracle all allow one to easily set up schemas that reflect the triple nature of RDF. One can then store any triple in those databases as if they were native RDF databases. The advantage is that the technology is well known. The disadvantage may be that there is one layer of abstraction more than needed, and so things may not be quite as fast or efficient as they would be in pure RDF databases. Finally, one can think of the vast amount of data currently in relational databases as being already RDF data. It suffices to create a mapping from the internal SQL schema to the ontologies one wishes to use. D2RQ is a tool in development that explores this strategy. Ask a query to a D2RQ endpoint, and it will translate that query into an SQL query, fetch the results, and present those in an RDF readable way. Let us now connect what we have learned to create a useful application. The best way, in my opinion, to explore in an immediately useful way the possibilities presented by the semantic web is to find a database that already has a number of faithful users. These will be querying the database through an HTML or Java client front end. Next, develop an ontology that reflects the data you wish to make publicly available. Strive to make it easy to understand and accessible by publishing it on the web. To save yourself and others time, it's a good idea to use other established ontologies. As always, don't reinvent the wheel. Next, make a SPARQL endpoint available that uses the ontology developed previously to access the data. You can do this either by using a tool such as D2RQ or by extracting the data and placing it in a pure RDF database that gets updated at regular intervals. This will allow robots, and engineers of course, to access the data from the SPARQL endpoint. The difference between the SPARQL endpoint and the web interface is that the web interface probably has very limited querying capabilities or will of necessity be an ad hoc solution. Standardizing on SPARQL means that engineers can use ready-made tools to work with the data and will be able to deduce the structure of it and the format of the queries by looking at the ontology alone. Now, what would such a robot look like? Well, it need not be anything very special, to tell the truth. I mean, it need not have legs and run around or make tea. NetBeans could be such a robot. If one were to open the Java issue database, then it won't take long to think of some good ideas for how to use this information. NetBeans could, for example, be extended to inform the developer about issues related to the classes he is importing. Here is what such an improved NetBeans could look like. I have placed some color-coordinated numbers in the margin of the property dialog class. This would tell the user that the javax.swing.jOptionPane class that is being imported has currently 5 issues, some of which are open, and that the java.net.uri class has 3 solved issues, etc. Clicking on such a number could bring up a very short description with hyperlinks to the web interface, where the developer could find out more information. There are probably many other interesting uses of the data one could think of. Imagine that the functionality offered by NetBeans becomes very popular. It will then be just a matter of adding a SPARQL endpoint with the same ontology to any of the other open source bug databases out in the wild. NetBeans will then immediately become aware not only of issues in the Sun Java implementation, but also with all these other open source libraries. It becomes clearer now why using RDF in a SPARQL interface is so useful. Let us now look at a more distributed way of publishing RDF metadata. Imagine our previous steps have been successful. By now we should have a large number of developers with a good taste for RDF. It will then become obvious how useful such metadata can be. It won't take long then before people start asking NetBeans to help publish metadata in an RDF-friendly way about the projects being developed. This is what O'Reilly's Code Zoo is attempting to do. But it will be most successful when tool publishers start integrating these facilities into the IDEs. The type of metadata of interest would be that which can be described by the DOPE ontology described earlier in this presentation. Who the project owner is, where the code repositories are, who the translators are, etc. Changes to the project would be published in an RSS or Atom feed. A spider could then crawl these feeds and place the data in a centralized metadata database. The spider could be part of the integrated development environment itself, or it could be a specialized service out on the web with its own SPARQL endpoint. This in turn will permit NetBeans to develop new, interesting, and yet unimagined features. So we now have a strategy for creating a structure to deal with the mythical man-month problem I described earlier in this talk. The beauty of this solution is that it can be built step by step, with technologies currently available and at a very low cost. Given the structure of RDF, we have something that should easily scale to the web, that does not require centralized control, and that is perfectly organic. As this comes to pass, we can imagine a world in which all that someone would need to participate in an open source project is to point their IDE at a jar or library and press a button. This would download the code, link them to a database, and set them up for work. They would then be able to decide if the problem is with the code being looked at, check if the issue is one that has already been reported, fix it if not, and with a click of a button send the patch to the current maintainer. This should dramatically reduce the friction in code development. It can't hurt to try. But this was just one example of what is possible by opening up a well-used database. There are many very large organizations, such as Philips, British Telecom, Air France, Siemens, covering every industrial sector in existence, that could, by increasing the ease with which developers can use their data, create new business opportunities for others to drive their sales. So in conclusion, here are the types of things any organization should do to get involved in the semantic web. First, open up a database with a SPARQL front end. It's probably worth starting with one that is of reasonable size in order to build up some internal knowledge of RDF. From usage of this database and feedback, it should become clear what exactly the needs in tools and hardware is. It should also be possible to establish best practice guidelines in ontology development. With time and investment, tools should be improving too. Some interesting things to look at may be standardization of object to RDF database mappings. I have developed something along these lines called RDF Hibernate that uses Java 5 annotations to make it very easy for developers to crawl the data graph using just simple objects. Good inferencing databases would be very welcome too. More SPARQL front ends, and of course good developer tool integration. As we get to use RDF, it will become more and more clear how widely applicable it is. This reminds me that file system metadata is another big topic on the horizon as Apple's OS X and Microsoft's Vista start introducing this into their OS. Solaris already has this built in, and the next version of NFS will too. A very good architectural decision would be to use URLs as the property of file system metadata, as that would fit in seamlessly with what has been described here.